All right, guys, I'm going to put this, like I said, record it. So just follow along, and if you have any questions at all, please, just jump in and let me know. This is pretty much the same thing that will be on the quiz on Monday or Tuesday if we're not here Monday, with, of course, not exactly the same, different numbers, different examples, or something like that. So, question one says, write an example of an equation that shows an acid reacting with a base. You could choose anything you want. You could even just do the generic acid base thing if you wanted to. Like, let's say, for example, if I have some generic acid, HA, whatever that happens, that could be that could be acetic acid, it could be nitric acid, nitrous acid. Matter of fact, let's make it a real one. Just HNO2. That's an example of an acid, nitrous acid. And if I put that in water, well, something's going to happen. This is going to give up the proton, H3O plus NO2 minus. And as long as you're good saying this is the acid, this is the base, this is the conjugate acid and conjugate base. So I think that you could work up some example, because that's going to be a question. It doesn't have to be this one. Could be. But if you have a different one, you have a favorite acid, go for it. So that's question one. Question two says, define the term amphoteric. And maybe you don't remember what that means, but amphoteric means a substance that can act as either an acid or a base. Okay? Think of ambidextrous, right? I can use my left hand or I can use my right hand. Although I just got that backwards. I could use my left hand or I could use my right hand. So amphoteric, I can be an acid or a base. A classic example would be water. Other things are amphoteric. So let's take a look here. This says the hydrogen sulfide ion is amphoteric, HSO3 minus. That means it can either donate a proton or accept a proton. Write an equation for HSO3 minus with water in which the ion acts as an acid. So if this is going to be the acid, that's going to give up the proton to the water. So I'll get H3O plus SO3 minus 2. Remember, if I take a proton away, I have to get another minus charge. Done. In this case, the acid, base, conjugate acid, conjugate base. Easy stuff. And the other one was write one where it acts as a base. That means it accepts a proton. HSO3 minus plus H2O. That's going to give us H2SO3 plus OH minus, because now the water is acting as the acid, which is true because water is also amphoteric. And that would be the base, the acid, conjugate acid, and the conjugate base. So I'll have something like this on there, but I'll probably choose a different substance instead of that. Something that is amphoteric. Like, for example, H2PO4 minus. That would be another one that can act like that. So that's question two. And this is one that question three is one that sometimes causes people a little bit of confusion. Because you have to remember pH and concentration of hydrogen ions. The higher the concentration of hydrogen ions, the lower the pH. So as this goes up in solution, that goes up, the pH goes down. Right? More and more acidic as we go from 7 to 6 to 5 to 4 to 3. So, and likewise, if the concentration of hydrogen ions goes down, pH goes up. So keep that in mind. Give an example of a substance with a low pH. That could be any acid at all. Hey, hydrochloric acid solution. You could say this If I have a 3 molar hydrochloric acid solution, that's going to have a very low pH. Very, very low. On a quiz, I might say, give an example of something with a high pH. What do you think a high pH might be? What kind of a substance? Is that a base? An example of a base. All else fails, hey, NaOH solution. I have an NaO 0.1 molar sodium hydroxide. Phew, that's going to have a high pH. Okay. Number 4, write the conjugate acids for each of these bases. In order to do that, all you have to do is add another proton, and for every proton you add, you have to adjust your charge. So if I want the conjugate acid of HSO4 with a minus charge, well, it's going to be H2SO4. One more proton, plus charge, cancels that negative charge, so we're good. Okay. SO4 with a minus 2 charge. Well, add a proton, you're going to get HSO4 with a minus 1 charge. And finally, if I have ClO4 with a minus charge, I add a proton, I get HClO4, and you end up with perchloric acid. Now, how could I make this different on a quiz? I could say, write the conjugate bases of the following. So an example of something like that, if I said, hey, H3PO4, what's the conjugate base? Well, you take away a proton. H2PO4 with a minus charge. What's the conjugate base of HNO3? NO3 minus. Perfect. See? You guys got this stuff down. So probably, instead of making it just like this, maybe I'll put, a couple conjugate acids, a couple conjugate bases. But again, nothing that you can't do. Number 5 is show that the pH of water is 7. And this you have to recall something. And I don't know if you remember, but I said, all right, in any situation, the concentration of H plus times OH minus has to be 1 times 10 to the negative 14. So we can use this, and you could also write that as H3O plus, same thing. So we can use this to solve for either one of these if we have the other one, which we can look at in number 6. But for water, we know that water, when it breaks up, when it autoionizes, we have H3O plus OH minus. And if I call that X and X, because they're 1 to 1, well then, just like we're used to doing, that would be, X squared. So I can say X times X squared is 1 times 10 to the minus 14. So if I take the square root of both sides, X is going to be 1 times 10 to the minus 7. And that's going to be either one of those. So that could be the concentration of H plus. And you know that if you want the pH, you take the negative log. So the negative log of 10 to the minus 7 is just 7. So then you just say, well, negative log of 1 times 10 to the minus 7 is equal to 7. So then you've proven that that is equal to your pH of water. It's pretty easy little thing to prove. Now, number 6, you could do one of 2 ways. And you could go ahead. They want pH. And sometimes they give you the concentration of hydroxide. Like, for example, and remember, pH is the negative log of the concentration of H plus. And so for A, they tell you that it's the concentration of hydroxide is going to be 7.23 times 10 to the minus 2. Now, what you can do, you can get the POH and subtract it from 14. To me, that's the easiest thing. okay? Or you could say, well, I know this value. I'll solve for that, and then I'll take the negative log of that. It gives you an extra. Well, I guess they both have two steps, but I think this one's a little bit easier. Just by looking at this, though, this is 10 to the minus 2, so this is going to be a basic solution, because if my concentration of OH minus is greater than 10 to the minus 7, it's basic. So let's go ahead and get the POH for that. I'm going to take the negative log of 7.23 times 10 to the minus 2. Does anyone else keep smelling coffee, or is it just me?
I think I just smelled it a little bit.
Yeah, I keep smelling coffee wafting in here for some reason. Okay, so let's take a look here. Negative log of 7.23 times 10 to the minus 2, and you get a POH of 1.14. That's POH. So the pH is going to be 12.85. Does that make sense? Yeah. So there you go. There's your pH. Very high, and of course you expect that. So that's easy. Next one says, you don't even have to do anything here. It says the concentration of H plus is 4.02 times 10 to the minus 13. Now, you look at this and you say, that's pretty small. That's a lot less than 10 to the minus 7. So this is going to be a basic solution. So we don't have to do anything except take the negative log. Negative log 4.02 times 10 to the negative 13. That's going to be pH. Negative log 4.02 times 10 to the negative 13. And you get 12.4. So there's your pH. Again, can't make this thing too difficult because it's just not. It's not hard by its very nature. The next one, you're going to have a pH which is mildly acidic because the concentration of hydrogen ions is 6.99 times 10 to the minus 7. So you're going to get a pH somewhere between 6 and 7, and probably closer to 6. So negative log of 6.99 times 10 to the minus 7 is going to be 6.2 if you round it to the 10th place. So a little acidic. And the last one, concentration of OH minus is equal to 1.43 times 10 to the negative 12. So you're going to say, well, that's a lot less than 10 to the minus 7, so this is going to be an acidic solution. Let's do this one the other way. Let me just show you in case you want to know. Okay, we know that the concentration of H plus times the concentration, 1.43 times 10 to the minus 12, is equal to 1 times 10 to the minus 14. So let's go ahead and divide through, and we'll come up with that. Then we'll take the negative log. So you get the concentration of hydrogen ions as being 0.007 molar. So we're going to take the negative log of that. And you get a pH of 2.2 if you round to the 10th place. Not bad, huh? Pretty good. Okay, let's keep on chugging. I think the backside's kind of fun. They have some different sorts of problems on there. So let me erase these. And question number 1 says, which of the following indicates an acidic solution? So, if you know that the pH is less than 7, that's certainly an acidic solution. So A is an answer. pH greater than 7, B, no, that's a basic solution. This one, the concentration of H plus is greater than the concentration of OH minus. Well, yeah, that's acidic because I have more hydrogens than hydroxides. So, and then last one, it says the concentration of H plus is less than 1 times 10 to the minus 7. That would be a basic solution. Okay, number 8 is kind of a fun one, I think. As an amateur chemist, which you are by this point, you chlorinate your hot tub with hydrochloric acid. Not that you would really do that. Put too much of that in there and go for a swim, you'll be in trouble. As an amateur chemist, you chlorinate your hot tub with hydrochloric acid to prevent the spread of unsightly dermatological infections. You find the pH of your hot tub is 5. What is the concentration of hydrogen ions and the molarity of the HCl? Well, HCl is a strong acid, so it's going to break up into this and this. So the concentration of hydrogen ions is going to be 10 to the negative pH. So that's just 10 to the negative 5, because the pH was 5 molar. That would be my concentration of my hydrogen ions. And since they all came from the hydrochloric acid, you started out with 10 to the minus 5 molar HCl. It's kind of a silly little question, you know. Number 9 is a weak acid. Weak acids, we have to use our little equation with x squared in it. And we are told that the Ka, well, first of all, that's x squared over the concentration of my acid that I start with. That's definitely one you should know. Or if you want to use like a little 3x5 index card, that's fine with me. I don't care. So we've got 1.8 times 10 to the minus 5 is equal to x squared, and the starting concentration is 0.3 molar. So solving it for x, and then getting the negative log, pretty easy. So 1.8 negative 5 times 0.3. You get x squared is equal to 5.4 times 10 to the minus 6. I'm going to take the square root of that, and I get x as being 0.0023 molar. Take the negative log. And I get 2.6 as my pH. And you'd expect that. It's a weak acid. Okay. If it was a strong acid, you would just take the negative log of the 0.3, and you'd see a much lower pH. Alrighty. Moving along here. Okay. Use the following acidity constants to answer the questions below. Now, the smaller the Ka, the weaker the acid. So all you have to do is compare these. The first one for acetic acid is 1.8 times 10 to the minus 5. The one below it, formic acid, is 1.7 times 10 to the minus 4. But the next one over, HCN, hydrogen cyanide, HCN has a Ka of 4.9 times 10 to the minus 10. So that would be the weakest of the acids. And then if you want the pKa, remember what P means? Negative log. So pKa is the negative log 4.9 times 10 to the minus 10. So it's going to be 9 something. Okay, negative log 4.9 times 10 to the negative 10, and 9.3. So this is just like when you talk about pH. The stronger the acid, the lower the pKa, lower the pKa. The weaker the acid, the higher the pKa, because of that negative log business. Okay, last two. Titration reveals that 11.6 milliliters of 3 molar sulfuric acid are required to neutralize sodium hydroxide, 25 milliliters of sodium hydroxide solution. What is the molarity? Okay, well, we have, remember, the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. The only problem here, guys, is that H2SO4 has 2 acidic protons. So really, the molarity of the acidic part is twice the molarity of the acid. Does that make sense? Because when this reacts with a base, it will react with 2 NaOH. So I have 2 protons there. So the only thing you have to remember is the molarity of the acid is effectively twice the amount that's shown here. So you're going to have really 6 molar in acidic protons times 11.6 milliliters is equal to, well, this is the base. I should have flipped this around. This is the molarity of the, wait a minute. Oh, no, that's the acid. Yeah, that's the acid. And then we have molarity of the base, which we're trying to find, times 25 milliliters. So multiply and divide by 25, we'll get the molarity of our sodium hydroxide. 6 times 11.6 divided by 25. And we get a 2.8 molar is the concentration of my NaOH. That makes sense about having more than one proton. You have to just multiply that by 2. If it was just HCl, for example, it would just be 1 proton. And then finally, the last one is a buffer question. And if you remember, we had an equation that helps us with buffers. Buffer, and by the way, the definition of a buffer is something that, a solution that resists changes in pH. So we're going to have the pH of the buffer is equal to the pKa of my weak acid plus the log of the concentration of my conjugate base, salt, divided by the concentration of the acid. This equation, by the way, I didn't tell you the name of it. It's called the Henderson-Hasselbalch equation. I don't care if you know the name of that or not, but that's the name of this equation. So we want to solve for the pH. So the pH is equal to 4.74. That's the pKa. Just take the negative log of Ka. And that's going to be plus the log of 0.3 over 0.1. So this number is going to be greater than 1, since this fraction is greater than 1. Matter of fact, it's going to be 3. So we're going to take the log of 3, and we're going to add it to 4.74. And we get a buffer of 5.2 pH. and it should maintain that pH right around 5.2 if you add some strong acid or some strong base to it. So that's our acid-base chapter, and we're all done. So, all right, hope this helps. If you want to watch it over the weekend, that would be great. If you don't, if you're good, that's fine too.